Hello everyone, you're all very welcome to Värt att veta, the lecture series that presents important research findings in a way that we can all understand. The series Worth Knowing is organized by the SLU Library. My name is Karin Benmarker and I will host this lecture today together with Lucia Hatamian and Jennifer Salomonsson from the library. You will be able to ask your questions after the lecture in the chat or by raising your hand. Please keep your microphones on mute as the lecture will be recorded. The recording of the lecture will be published on the Worth Knowing website later. Today, we're hosting Cecilia Lalander, researcher at the Department of Energy and Technology, who will give a lecture about a waste management method that follows the principles of a circular economy through fly larval composting. Cecilia has a PhD from Monash University in Melbourne, Australia, and she has been a researcher here at SLU since 2011. And apart from the work with fly larvae composting, Cecilia also works with different biodegradable waste fractions, such as food, toilet, and food industry wastes. Cecilia also teaches the courses Waste Management and Sustainable Technologies for low and medium income countries. So now we're eager to hear more about the topic of the day. So please, Cecilia, I hand over to you now.
So thank you for the presentation. So like has already been said, my name is Cecilia Lalander. I am an associate professor in environmental engineering, and today I will talk about how we can turn waste into food. So if we start from the beginning by the definition of waste. What is waste? Well, the definition of solid waste management, according to the Encyclopedia Britannica, is the collection, treatment, and disposal of solid material that is discarded because it has served its purpose or is no longer useful. So I want to just stress this, that it's considered something that has served its purpose. It doesn't say anything about it having been degraded or bad or broken. It's just that the owner of the item or whatever it is no longer wants it, therefore it's waste. So if we go into, since in 2015, the EU Commission launched an action plan for circular economy. So what that means is that the EU Commission wanted to find a way of transitioning to a circular economy. So what is a circular economy and how does that differ from what we have today, which is a linear economy? Well, in a circular economy, we don't really have any waste. That's the idea, the hope that the waste product from one process becomes the substrate of something in another process, and therefore it goes round and round. So it's called that we want to circulate with the system within, so that we minimize the input from external input of virgin resources. So we want to utilize what we have much more efficiently. And there, if we were to burn something, incinerate it, then or just dump it and not put it back into the production, it's a leakage, and it's then therefore not part of the circular economy. So how should waste be managed then? Well, in this action plan, a directive for how waste should be managed was included, and it's called the waste hierarchy that you can see here in this picture. So what this shows is the preference that different waste management methods should have. So at the top of the hierarchy, we have the measures or strategies that should have highest priority. And the lower down in the hierarchy we go, the least priority the method should have. So at the top, we have prevention. So just not consuming as much, preventing the waste from actually being formed is at the the top. That's what we should prioritize. And at the bottom, we have disposals, as in landfill or something like that. And again, if we go back to the definition by previous definition of circular economy, that means that prevent, reuse, and recycle are the only strategies that are actually part of a circular economy. Recover and disposal are not. So what are we throwing away? If we look at this globally, what we are throwing away here, we see we have food and garden waste, we have glass, metal, paper and cardboard, plastics, rubber, wood, and then others. But we pay some special attention to this food and garden waste, which makes out globally 44% of what we throw away. And how are we treating the waste today? Well, we are composting some, we're incinerating a bit. This is on a global scale. This is not what happens in Sweden. And then we have these blue colored ones, which is controlled landfills, sanitary landfills, landfill, open dumps. So what that means is that 70% of the waste is actually being disposed of in some way and not utilized in any sort of way. And if you remember from the previous slide, 44% of our global waste is organic material or biodegradable material. So why do I think this is a problem? Because I do think it's a problem, and now I will tell you why. So when we have the degradation of biodegradable material in the presence of oxygen, we have respiration. This is pretty much what happens in our own bodies when we consume food, although we don't consume waste, but you understand. And then we form carbon dioxide and water, and a lot of energy in form of heat usually is formed. So this is an aerobic composting process where you respire the waste into carbon dioxide and water, and you have a compost that contains plant nutrients. Now, if we were to remove the waste, the oxygen, what we have, we can't respire it as efficiently, so we will go through other paths, and we will have methane and carbon dioxide and water form, and very little energy. The energy will be stored in this form, so we have in the methane, because that is an energy-rich molecule. And we will also get plant nutrients, organic acids, alcohols, and other substances. So if we look into this methane, as we know, it's a greenhouse gas. Carbon dioxide is also a greenhouse gas. So what is the problem with having another greenhouse gas? Well, if we think that this material, this organic waste, is actually part of the biogenic carbon cycle. So it's not adding on a new carbon emissions into the atmosphere. We're using what's already there. But so that's contrary to, for example, burning oil or plastic or something like that. We're actually contributing to putting additional carbon into the carbon cycle. However, methane is a more potent greenhouse gas, so it keeps more heat than carbon dioxide does. So if we can shift it from producing more methane to producing more carbon dioxide, then that is better. Then we have the water here, and in the water we can have plant nutrients leaching out. So if we have the plant nutrients in the water phase, and that leaches out into the environment and goes into a water body of some sort, that can lead to eutrophication. So that means that we will have a lot of growth in the water, and the oxygen that is available there will be depleted, and we will have like dead zones and so. And it can also, the disease-causing microorganisms can also be found in the water here, and therefore can lead to disease transmission when that water is let out. So this is a picture of what can happen in some parts of the world. Here we have the the Katisi landfill in Kampala, the capital of Uganda. And here we can see how these waste pickers, they are going around looking for valuable fractions in the waste. And we actually know that 45% of the total waste management today is handled by the informal sector. So the informal sector is a sector that is not part of a municipality or not part of a more official employment, but they are doing it as a means of surviving. So what they pick out are the valuable fractions. So that could be the metals, some high quality plastics, or something that has a value that they can sell. So what they leave behind is, of course, that's not so, of course, what they leave behind is the biodegradable fraction. And I guess that's also what these birds are looking for. So the biodegradable fraction is left behind, and there it decomposes anaerobically. And it has been estimated that 3 to 5% of the total anthropogenic greenhouse gas emissions actually originate from these open dumps and landfills. So it's quite a high proportion of the greenhouse gas emissions that come from these inadequate waste management strategies. That in fact is at the bottom of the waste hierarchy. So if we were to look in Sweden, what happens in Sweden? Well, what we know, this is from Avfall Sverige, from 2020's statistics. And what we see that in Sweden, we produce about 500 kilograms of waste per person and year. And we can also see that 38% of all food waste is sorted out. So another way of seeing that is that actually 62% of our food waste from household is incinerated. Because it is not sorted out, it goes with the mixed waste and it's incinerated. So if we go back to this circular economy, how are we doing? Well, in Sweden, we're recovering energy in the form of heat, and that is actually not part of the circular economy. Globally, we're doing even worse. We're just dumping it or landfilling it at the bottom here. So currently, we are quite far from a circular economy when it comes to the biodegradable waste. So going back to the waste hierarchy, the 38% of the food waste in Sweden that is being sorted out is to the greatest extent digested. So we are having this anaerobic digestion. So we are not having this degradation happening without the oxygen, but we're doing it in controlled form so that we can utilize the methane and we use them as vehicle gas. So that's how the buses here in Uppsala, for example, are run. So that's a positive thing, one could say, but the digestion end up somewhere here in the waste hierarchy because we are recycling plant nutrients if we are spreading the digestate, while the energy in the biogas is being recovered in the form of vehicle gas. If we were to compost that biodegradable fraction, well, then we are recycling plant nutrients, basically. Is there a way of moving up in the waste hierarchy when it comes to food waste? Can we reuse the food waste, for example? What used to happen when I was a kid, the food waste was given to pigs, and they would eat the food waste rather than throwing it away or just burning it like we're doing today. So that is a direct form of reuse of the food waste. However, after the mad cow disease, this is no longer, that happens in the 80s and 90s in the European Union. This is no longer allowed. So our food waste is not being used to feed animals anymore, but it's actually mostly being burnt. So what happens in nature? Well, what happens, as you can see in this very beautiful illustration, is these macroorganisms like the larvae of beetles, of flies, and so on. They grow, in this case, a cow manure, and then the larger animals, such as the birds, different types of birds, and so on, they pick out these larvae, these insects and eat on them. This beautiful illustration comes from this very informative book, Kalas i komockan by Inger Kjellander. It's a party in the cow manure if you don't understand Swedish. It's a very good book for learning about one natural system. So could we imitate that somehow? So instead of giving the food waste directly as animal feed, we give it to insects and then we give it to animals. Would that be considered reuse or indirect reuse of complex molecules or amino and fatty, such as amino and fatty acids? Or would it more be considered recycling of complex molecules? We don't know, there is no clear definition, but at least we are higher up in the waste hierarchy because we are recycling or reusing these complex molecules. And it's definitely part of a circular economy. So this is what we're doing. This is what my research is about. It's to engineer a natural process. So how do we do it? Well, we take this 1 milligram larvae, we put them in some waste substrate. We wait for 2 weeks and then the larvae have grown and they now weigh 200 milligrams. So in other words, they have increased their weight by 200 times in 2 weeks. So the insects that we used the black soldier fly, the Hermetia illusions, and that is a tropical fly. The reason why we use a tropical fly has to do with their life cycle. So this, as you see here, this is the time when they are in their larval stage. That's where we want to use them for our treatment. In nature, these flies, these larvae that originate from the south of the US, they come from the American continent. They would crawl out from the waste in this stage that is called prepupa. So it's still in the larval stage, but they have already changed their morphology some, and they crawl out to find a dry and a dark site for pupation, and then they pupate, and after about 2 weeks they emerge as the fly. And then these flies, they procreate and lay eggs, and the eggs become the larvae. Now, they stop feeding already in this stage. So these larvae, that's one of the reasons why we want to use these tropical flies, because they are not considered to be vectors for disease transmission. Because if you think of another fly larvae or a common house fly or something like that, you think they are at your food and then they go to a pile of manure and then they come back to your food, and in that way they're transmitting diseases. But these ones, because these don't feed as adults, they are not vectors for disease transmission. The other aspect, as you may notice, is that they're quite large, these larvae, and they're considerably larger than other fly larvae. So that means that they are simpler to separate from the treatment residue. Now, this other part here is part of a colony, because you need to have a colony to produce these small larvae. But these are the ones that I will focus on, this part here. So how efficient is the process? Well, if you have 1 ton of food waste, you will get around 250 kilograms of larvae. And these contain, this is roughly 35 kilograms of crude protein and 30 kilograms of crude fat. So if we look closer into that, the protein content, that adds up to around 40% on a dry matter basis. So of the total dry matter in the larvae, 40% is protein. So if we compare to other protein sources that are commonly used in animal feed, it is at the same protein content as soy, and soy is what is the most commonly used protein source in feed today. It is lower than fish meal. But when you look at a protein for animal feed, it's not only the protein content, it's also the composition of the protein that matters. So if you have the amino acid composition matters. And one of the amino acids that is really important when we look at this is the methionine. So it's these sulfur containing amino acids that are very important for predatory fish, like salmon, for example, and also for poultry, because they need that for their feather production, among other things. And if we look at the methionine content, we can see that it's considerably lower than fish meal, but it is higher than soy. So it is still an interesting protein. It still has an interesting protein composition. We also see here that this is an error bar, so that means that these larvae that these analyses are based on, they've been reared in some different substrates, and in different substrates that we can play around a little bit with substrates to modify the methionine content of the larvae. And if we go to the fatty acid profile of these larvae, because like I was saying before, the larvae, they have to accumulate all the energy that they need for the entire life cycle as in the larval stage. So these larvae are quite fat compared to other insect larvae. But the rearing substrate in which the larvae are reared really has a huge impact on the fat content of the larvae. So they will you see here a larvae reared in bread has a very high fat content compared to larvae reared in food waste, for example. Considerably higher fat content. So a larvae reared in food waste might have a fat content of around 30%, whereas the larvae reared on bread can be around 50%. So it really, there we can really modify the composition of the larvae depending on the substrate. But if we look here at these colors, we see that these are the composition of the fatty acids. And we see here the SFA, that's saturated fatty acids. So regardless of what the larvae have been fed, they always contain mostly saturated fatty acids. So what we have learned is that also that the fat content increases with larval size, or actually it's more like age. They accumulate the fat later in their larval stage, and that high carbohydrate content will result in very fat larvae, and that they consist mostly of saturated fat. And if we look at, we don't only have the insects, we also get the treatment residue. This is called the frass. So that's kind of what has not been consumed by the larvae, and their feces, the larval feces, and some of their skins, because the larvae, they molt, they change skins 6 times in the larval stage. So if also we see in the process that 250 plus 200, that doesn't add up to 1000, but a lot of water leaves in the process due to evaporation, and you also have the respiration, so you have some carbon dioxide forming. So if we look at the other, now we've looked at the larvae fraction, now let's look at the frass. What can we do with the frass? Well, we've made some trials, and here we see that the Swiss chard, which is mangold, grown in with different fertilizers. So here we have just unfertilized, the control with no fertilization, cow manure, NPK fertilizer, which is a chemical fertilizer. We have BSF frass reared in feces and BSF frass reared in food waste. And what the take-home message here is that we have a very similar yield when we use the frass as when we use the chemical fertilizer. So there seems to be some potential in using this frass. Now, other researchers have also shown that we don't have to look only at the frass, we can also look at the larval skins, or example, the adult flies that comes out from the colony, that they also have an interesting potential as a fertilizer. But then we have this other, which is the most interesting part of using the frass or any mostly any organic fertilizers, is that we have something called biostimulants. So what biostimulants are different sort of hormones and microorganisms, substances that actually kind of communicates with the plants, and they can have different impact. So they can increase the resistance to abiotic stress, they can enhance the growth, they can increase nutrient uptake without actually increasing the nutrients in the soil. So what's written here in green, these are things that have been proven to have an impact by these substances, but the ones in red are things that they still, it's believed to be so, but has not been proven yet. But what the point is that these organic compost, they have also a high, they have other benefits that not just the nutrients themselves. The frass also actually turns out that it's quite unstable, that it's not a biologically stable process like a compost that has been matured. So there's still a lot of energy left after the larvae has consumed the waste. So what that means is that we can also digest it and get the biomethane out of it, so we can utilize all the resources most efficiently. So ideally so what we see here is this is just raw food waste, food waste, and here is the BSF composted food waste. And we see that the potential of biogas production has been reduced by about 30% per gram of organic matter. So we have there is still a lot of energy left in the residue, and we can extract the gas from there. So in an ideal situation, we could consider having a fly larvae composting happening before a digestion, and then we get we can capture more of the resources in the waste. And then of course the digestate after the fertilization, after the biogas process, can still be utilized for recycling the plant nutrients. So then we are really capturing all the different resources in the waste. Another benefit of this system is that it has lower greenhouse gas emissions than a regular windrow composting. So here we see the biogenic carbon dioxide emissions. And of course, the reason why this is lower is because a lot of the carbon goes into the larvae. And to be fair, once the animals consume the larvae, this carbon will also have been formed into carbon dioxide. But regardless, we just look at the actual process, then here we see that the emissions are lower. But the most interesting part is not the carbon dioxide. As I said, it's already part of the most interesting is the methane. And here we see that it's negligible, the methane and the nitrous oxide emissions from fly larvae composting, whereas in regular windrow composting, we can have substantial emissions of these greenhouse gases, and that's because we have anaerobic pockets in the pile. If we look also just at the environmental impact of using these substrates, here we see the environment. This is higher environmental impact and lower environmental impact. And when we look at the larvae, so if we make feed of larvae reared in different substrates, then what is the environmental impact? And what we see here is that they can have it really differs depending on what we feed the larvae, the environmental impact that it will have. So if we compare the baseline on giving them rye meal with just conventional feed, we see that it's actually not beneficial to rear the black soldier fly larvae on something that we ourselves can eat. It actually will have a much higher environmental impact than conventional feed. So if we go back to this picture and we see this is the environmental impact of conventional feed. So for this process to be of environmental benefit, we have to rear them on some sort of waste product. And here we can see municipal waste, we have a negative environmental impact, which means that it's a benefit to form it. So it's very important also to consider what we're actually feeding our larvae, whether or not this is something that is beneficial or not. We've looked at the reduction, what happens to pollutants in this system. So if we look here at the microbial pollutants, we have seen that the reduction, that they reduce Salmonella, which is a zoonotic bacteria that it infects both animals and humans. So it's a problematic bacteria to get on a farm, for example. But here in this process, we see that we have a very high fast reduction when we do the fly larvae treatment, but and considerably faster than when we don't have any larvae in the treatment. Now that has also been, we also saw that that was the case for environmental pollutants such as carbamazepine, which is a very stable, it's a pharmaceutical that is very stable and found in most water bodies around the world. Because in water it doesn't degrade at all, but if we put it in our fly larvae composting treatment, it has a half-life that is lower than less than 2 days. So it's a very rapid degradation of this. However, we know that not all parasites are that not all disease-causing organisms are inactivated in this process. So it's still not a sanitization method, but it's a very biologically active little chamber. So a lot of these both pharmaceuticals and microorganisms that causes diseases are inactivated in the process. So what impacts the treatment? We look at different parameters when we design our treatment. So we look at how many larvae we put in, how much we feed them, when we feed them, and other things. And we are always limited by the size of the larvae. They only feed at the surface. So we have to have very shallow layers when we make our, when we design our treatments. And I want to just show you here what the impact of these parameters can be. So here we have a low larval density, and here and then a high larval density. And here this is food waste that has been composted for the same amount of time, but with different amount of larvae. And you can see how huge the difference is. In here, it hasn't barely started, but here they have already processed the material and it looks completely different. So that's just to show you what the parameters we play around with, what impact it can have on the process. And then, so the system that we have designed, like I said, we are limited by the size and that the layer that we can work in. So we have very shallow layers. We work in these kind of look like bread boxes, and we into this bread, which is 60 by 40 centimeters and about 12 centimeters high, we put 15 kilograms of food waste, or 1 kilo per day, which is the equivalent of that many people, which I don't remember exactly how many people that is. And then in order for it not to take up all the space in Uppsala, for example, we stack them. So we use these stacks where we stack 11 layers on, so we can treat 12 kilograms per day on the same area as one box. And that is equivalent of 400, the amount that we can treat in one of these racks is the same as 460 people produces in 1 day. And then we put these stacks into a freight container, and that in that we can produce, so in total we can have a container, one of these full-size 40 feet containers, we can treat 500 kilograms of waste per day in that container. So I want to just quickly talk about a project we did recently, because we have some limitations currently in what we are allowed to feed the larvae in the EU. So we are actually not allowed to feed them. They are considered farmed animals. We're not allowed to feed them anything that has animal byproducts. We're only allowed to feed them vegetable substrate and some former food stuff, but nothing that may contain meat of any sort. So that is quite limiting. So in a project that we did recently called 5 tons fish in the counter, we had to use food industry waste streams. So in that we used vegetable cuttings from Grönsakshallen Sorunda and reclaimed bread from the supermarket, bread that has not been sold at the supermarket. And then we put them into this treatment container that we have built with our stacks here, and gave them these 2 fractions and reared the larvae. And there we dried the larvae, we pressed the protein fraction out and made a pellet that we fed to trout. And then the frass compost we had spread Ultuna permaculture, took it and used it in their cultivation. But what we managed with this system, we have a 20 feet container, so a half-size container. So we managed to produce, in that we can totally produce, treat 250 kilograms per day. And then we get 48 kilograms of larvae per day, and 28 kilograms of frass. But if we were to use a full, or actually we would have to have 4 of these half-size containers, or 2 full-size containers to treat 1 ton a day. And if we were to do this, what we would get out is 54 kilograms of this larval protein meal. And we wanted to estimate what value we have in this product. So if we use kind of the value that we have on the market now, that we can sell that meal for 20 crowns per kilogram. So that adds up to about 1,000 crowns just for the protein meal. And then another 300 crown for the frass compost. And we could get a waste fee for treating the waste. So in total, we could look at getting a value of 2,280 crowns per ton of treated waste. So that's what we have to play around with when we design our systems and when we go forward. We did identify that this is a little bit challenging because it's a quite time-consuming process, but we are still quite positive for the future, and how this can play a role in really closing our loops, and also being an economically viable treatment method for the future. So with that, I would be happy to answer any questions that you have.
Okay, thank you so much, Cecilia. This is super interesting to hear. Do we have any questions in the audience?
Hi, I work at Johannes Stadsodlingar. We do aquaponic farming, and we're interested in insect farming based on our waste as well. So I was just curious about this frass. Do you know what they thought of it, the Ultuna permaculture?
Yeah, they really liked it, and they wanted more, because we gave it to 2 different, actually, not just to them, and they would have wanted more. And I know that they used it in their more commercial parts of their. We thought that they were going to use it for their more degraded parts, where just the edges, but they actually ended up using it in their where they produce more of the commercial crops, and they liked it a lot. Although I know that there is some that because that frass is not fully stable and you cannot add too much of it. It's not like a regular compost where you can just dump a lot. You have to use just a little, otherwise you can burn the plants and do. But they did that because they have a lot of green compost, and then it worked really well.
Did you pasteurize it, the frass, or was it as is?
No, we didn't do it in this, but it has to be done according to EU legislation if you're doing it.
I'm just curious.
Yeah.
Tack så jättemycket.
Yeah.
Well, I'm just curious to see, to hear a little bit about, what large scale benefits are you hoping for? I mean, what is your aim with the whole project? What do you see in the future that we can use? Will we all eat of this protein, or?
Well, we don't eat it. We eat the animals that eat it. So I don't know if we will notice so much because the benefits that these feeding them insects, if we were to feed it to fish or to chickens, for example, the benefit is that you can have the animal welfare benefits. You also improve there is evidence that you improve the gut health of both fish and the poultry by feeding them some insects, and it doesn't have to replace their whole protein source, but just by having an added benefit, they improve the health of the animals. And you could also give it as an environmental sort of stimulant for the chickens, because it is allowed to feed them live to chickens, and if you feed them live, they will activate the chickens, and therefore have another, apart from the health benefits, they could also have a welfare benefit to activate the chickens. So I see that as really interesting for organic farming, for example, that has a problem in supplying the methionine to their chickens, and currently they have to give a certain amount of methane of fish meal, because they're not allowed to use synthetic amino acids. So in that, I see it as very interesting for the organic poultry sector, but I also think it's very interesting for the fish sector to become less reliant on soy primarily. That is what they are using, and that it could have health benefits also for the fish. So if I were to dream, we could, because I can show you, this is a little bit of the potential that we have in Sweden today if we weren't limited by the legislation as we are today. Today in Sweden, we consume 14 kilograms of seafood per person and year, and we produce 130 kilograms of food waste per person and year. So if we imagine that we were to just produce larvae from this, then we're producing about 20 kilograms of protein, no, 20 kilograms of larvae per person a year, and that amounts to 3 kilograms of protein. So we could actually produce 7 kilograms of rainbow trout per person and year if we were to use all the food waste in Sweden. I mean, it's just a highly theoretical calculation, but it's just to show what is possible, like what we can do. And instead, if you keep in mind what I said, that we are actually incinerating over 60% of this, and what we are incinerating, we could be producing food with. So it's so in my vision of the future, I see that we are utilizing our waste in a much more efficient way than we are today. And we are reducing our waste, even though that's not my topic, but 500 kilograms per person a year is just too much. Like, we have to stop consuming, and we have to, the waste that we do form, we just have to utilize more efficiently, because we are really not very efficient in how we deal with the waste today.
Okay, thanks. We have a question here about, do you have any ideas about how to automate the process?
Yeah, I think what we have identified is that one of the main things that could need to be automated is the harvesting of the larvae. I mean, I think that that's not a very difficult, I think that this is already done for other fractions. So just by teaming up with some engineers, I think there's really not a big problem there. Of course, you could have like automated feeding, but the question is, when do you over optimize, and what parts do you really need to consider? So what we have identified is that the harvesting is actually one of the most time-consuming parts of this treatment, and that would really benefit from optimization. The other thing is that it's a bit time-consuming but now when you deal with the food industry waste, which is more difficult than if you deal with household segregated household waste, is that you need to collect its fractions. In some cases, if you use, like when we use the bread from supermarkets, we had to unpack the bread. And I know, I mean, there are machines that you can just put the whole thing in, and then they open the bags and you get the bread out, and you get the, so those are the most, like the substrate preparation can be demanding, but I think that the most important is the harvesting of the larvae. That's the most time consuming part, and I don't think it's difficult to find to automate it.
Yeah, that's interesting. And what about the I mean, getting the payoff out of this? Is it actually enough with the cost? I think you said was 2,280 crowns.
No, it's not enough. Well, it is enough if you get the waste, if you get paid for the waste as management. Because the waste management is a service, and you're providing a service, and you have to be paid for that. But if you view this as you're being an insect rearer, and you have to pay for your product, pay for the feed, then it's very difficult to find the economy in that. So that's also, so not only the environmental benefits are dependent on what substrate that you feed, but also the economy. So it kind of has to go into more waste management for it to be more economically viable. But I think that the bigger problem here is that we are still, the large part of society is not circular, it's linear still. And that means that we are extracting virgin products, and we're not paying for the production of those products, and then selling that at the price that is impossible to achieve with a circular system, because in a circular system, you pay for every aspect, every part of the production chain. And so it's much more expensive. So as long as we have this linear society, it's very difficult to achieve a viable process. But you can still work with these the benefits, the added benefits that you have, that you, like I was talking about the biostimulants in the frass. I mean, that is something that chemical fertilizer does not have, these biostimulants. So you're adding it's an added benefit, so you could charge more for it than you, for example, or the health benefits of using the insects for feed production. So maybe it's not the only feed, maybe it's pro fee, like just an added amendment that is at a higher cost. So you could have those kind of things coming out, and selling it also as more environmentally friendly, and also for health aspects of the animals and so on. So you have to tap into that. But it's still problematic when we have these linear flows to compete with.
I see. Thank you. There's another question here, Cecilia. Can you tell us a little bit about the energy consumption?
Yeah, it's a very relevant question. If these, as you understand that these environments that these larvae have to be in are warm, since they are a tropical fly. So we keep the treatment at 28 degrees, and we keep the colony at also around 28 degrees. But the thing is that can be done in a very good way, or it can be done in a very bad way. So it could be done in an uninsulated greenhouse, for example, and using fossil fuel sources to heat the greenhouse. And if you do that, you lose all potential and environmental benefit. And also, if you use a substrate that we can consume ourselves, of course, that will also lower the benefit of it. But in this, as you saw, we are now using these freight containers, and they are insulated. And in that, we also use, we have a heat exchanger. So we are heating up the outgoing air, heating up the ingoing air with the outgoing air. So there you reduce the energy consumption a lot by having that. And also the colony is, we don't heat it that much. We have the LED lights for the flies, and they are LED lights, but they still heat up the environment, and also keeping that more insulated. It doesn't have a huge energy consumption. But what we have a lot in Sweden today, we have a lot of waste energy. So we have a lot of very energy demanding industries, and they are producing heat that is just being kind of wasted today. So if we can tap into one of these waste energy streams to heat up our process, that would be even reduce the impact even more. So there are many things we can do to improve the energy usage. or reduced energy usage in the process.
I really like
Okay.
that you think globally in the project, that you check the energy, the people and everything in a very ecological way. It's very, very interesting.
That's what we try.
Yeah, thank you. Well, this was all very interesting. Please join us for the next Worth Knowing. This is organized by the Umeå Committee, and it's about skogens bidrag som kolsänka och förnybar resurs. I'm sorry I didn't get that in English, but then and then on the 5th of May we will have another Worth Knowing, that's called Who is the Park For, with Marit Jansson, a landscape architect from Alma. So thank you very much to everyone who joined us today, and especially to Cecilia. Hope to see you soon. Bye.
Tack så mycket.